very much.
Okay, thank you.
Okay, we're good to go again.
Okay, so this is about two approaches to fractal dimension. So the point to set principle, which was mentioned yesterday, is a bridge between these two approaches. So the first one is measure theoretic, which we call classical, and it asks how strongly granularity affects the size of covers, or some variation on that. As you zoom in on a shape, how many more cover elements do you need? And the other is algorithmic information theoretic, based on Kolmogorov complexity or martingales, and asks how strongly precision affects the length of programs. So let's start with the classical measure theoretic approach and a few notions of dimension that we're going to be concerned with here. So the first is Minkowski dimensions, or box counting dimensions. And they're called box counting. I'm going to do it with balls here. In fact, it doesn't particularly matter whether you use boxes or balls, or sets of limited diameter, and it can be a packing or a cover. This is a very robust definition, at least in well-behaved metric spaces. So if we let n of E delta be the minimum number of delta balls to cover E, then we can talk about the lower Minkowski dimension, which is the infimum of S's, where if you take the lim_inf of that number of balls times delta to the S, you get 0 at the end, right? So for small S's, that lim_inf is going to be infinite. And for big S's, it's going to be 0. And the point where it jumps in between those two is what we call the lower Minkowski dimension of the set. There's a phi here that you should ignore. Okay, and then the upper Minkowski dimension of the set is just the lim soup there. Okay. So this is a kind of primitive notion of dimension because it's forcing these cover or packing elements to all be roughly the same size. It has some unfriendly mathematical properties, including that it's not countably stable. Okay, so if you have a countably many sets, then the Minkowski dimension of their union isn't necessarily the supremum of their individual Minkowski dimensions, which is mathematically problematic. Okay, so we have some more sophisticated then notions of dimension, with the most famous being Hausdorff dimension. So what you're essentially doing here is just allowing all these cover elements to have different sizes that just have an upper bound. Okay, so instead of just summing up the number times delta to the S, we're going to sum up all of their individual diameters to the S, and we still have a cover of this, and then delta is an upper bound on the diameter. And then we're going to look again at the infimum of the S's, where this ends up being 0, and you get this same infinity to 0 jump. And for some classes of nice sets, including self-similar sets, which are some of the most familiar fractals, this is actually equivalent to either of the Minkowski dimensions. But for more exotic sets, it won't necessarily be. Now, the second most studied notion of dimension is packing dimension, which is dual to Hausdorff dimension in some sense. And now, instead of covering the set with a whole bunch of small sets, you're packing in balls that all have their centers inside the set and have to be disjoint. And then there's a couple steps here, but you do a similar thing of you get an outer measure out of that, and then you look at the S for which that outer measure jumps from infinity to 0. And you call that the packing dimension of the set. Okay, so that's the classical approach, but naturally we're more interested in the algorithmic information one here. So this is based on Kolmogorov complexity, which this audience is familiar with. But in particular, we need to do Kolmogorov complexity in Euclidean spaces, or more general metric spaces here. So in dimensional Euclidean space, we're going to say that the Kolmogorov complexity of a point X at precision R is the minimum complexity of a rational that's within a 2 to the minus R ball of that point. So with that, we can look at this ratio of the complexity at precision R of X over that precision R, which you can think of sort of as an information density at precision x, and then we can look at the asymptotic behavior of that ratio, of that density. And we can define the dimension of this individual point to be the lim inf of that density, and the strong dimension to be the lim sup. So for example, if x is computable, then you're going to get that both of these dimensions are 0. And if x is random and lives in dimensional Euclidean space, you'll get that both of these dimensions are n, and the converses do not hold there. We'll also need to use relative dimensions, so we'll just do this relative to an oracle. So we just give the decoding Turing machine access to some oracle W here. And often we'll want that oracle to encode some other point. And notice, for example, that if you have any point x, its dimension relative to itself is going to be 0, because you can get very short descriptions of x when you have access to an oracle for x at any precision you want. Yes?
So point for one, your metric definition that you have coincides with the binary representation. The dimension will be equal to what we call the dimension for the binary sequence that describes the binary.
Right. So that's true in Euclidean space, at least, because the differences are sublinear and you're dividing by this r, right? It starts getting more fragile as we move into gauges and infinite dimensional spaces, but yes, generally true. Okay, so this is the original instances of the point to set principle, is that you can characterize the classical Hausdorff dimension as the minimum overall oracles of the supremum overall points in the set of the dimension of the point relative to the oracle, and similarly for packing dimension with strong dimension. So this lets us reason about the classical fractal dimensions of the sets just based on the compressibility or asymptotic information density of the individual points within the set. So this has been used in various ways. These are some of the ones I've been involved in. Yesterday, you saw a few more examples by Don Stoll and Jack Lutz and Ted. It's been particularly useful in my work, at least, for eliminating assumptions that a set has to be analytic. That a lot of the classical arguments about how a lot of the classical arguments for bounding fractal dimension somehow use arguments from analysis that need some nice structural properties of the set from compactness, Borel, or analytic or something. And this point to set way somehow removes any sort of smooth set-based assumptions like that, and lets you prove these things for general sets. So we can get these nice general theorems about how Hausdorff dimension interacts with itself and how it interacts with packing dimension. They're really at the foundation of fractal geometry. Okay, so but this talk is about extending this beyond just Euclidean spaces. And the first way I'm going to talk about is extending the reach to arbitrary separable metric spaces. So yeah, I mean, there's been quite a bit of work on this in Euclidean spaces or sequence spaces over finite alphabets, but we'd like to do geometric measure theory in other domains. So we're going to do two things here. We're going to extend the point to set principle to any separable metric space, any metric space that has a countable dense set. And then we're also going to extend it to gauged dimensions, which I'll define in a moment, which you need to use to talk meaningfully about dimension in infinite dimensional spaces, and can also be used to talk more precisely about dimension. Okay, so here's what I mean there. So any standard classical fractal dimension is some variation on, you want to find the smallest value s, or the inf of s, such that the sum of all the diameters to the s in a cover or a packing can or have to be small. You're doing something along those lines. but we can replace this diameter to the S thing with some other function family phi sub S of the diameter. And you could do this with any single parameter function family that is continuous, non-decreasing functions, and where you have this behavior that if S is bigger than T, then phi S of delta is little o of phi T of delta as delta approaches 0. This is a very straightforward generalization. And then we can do this in separable metric spaces. Sorry, we can take the algorithmic information approach in separable metric spaces by defining k sub delta of x to be the minimum complexity of a point D in the dense set, such that D is sufficiently close to x. Notice I've switched up here where the subscript in the k now is a continuous delta instead of being r representing delta equals 2 to the minus r. And then we can define the phi gauged algorithmic dimension to be the smallest s such that the lim inf as delta approaches 0 of 2 to the k delta of x times phi s of delta is 0. And similarly for the phi gauge strong algorithmic dimension with the lim sup. Now, okay, so I've swept under the rug a little bit here the issue of prefix complexity versus plane complexity. So all this stuff was originally done in prefix complexity, K. And for maximum generality in this setting, you actually want to use plane complexity. But for most interesting examples, prefix will do as well. Okay, so here's the general point set principle. Let X rho be a separable metric space and phi a gauge family with some modest conditions, and let E be any subset of X, then we can say that the phi gauged Hausdorff dimension of E is the minimum over all oracles of the supremum over all points in the set of the phi gauge dimension relative to this oracle A of the point. So this lets us do the exact same thing, and similarly for packing dimension. Yes, Arno.
Would this be a theorem or a?
Sorry?
Do you have a theorem here, or is it a tradition?
This is a theorem. Yeah, I mean the phi gauge Hausdorff dimension came predefined, and this was the definitions of the phi gauge algorithmic dimensions, and this is showing a characterization of one in terms of the other. Thank you. Oh, no, not okay. I mean, it's basically that you need these gauge families to not be jumping around too much in S. But I don't remember the exact quantitative characterization here. So we had that as one of the parts of the definition of the gauge family. You may need an additional factor of 2 there. So this, I mean, what happens here is that as things start getting like really, really close to each other, all of the basic theorems in fractal geometry, including that, Minkowski dimension is robust, start really breaking down, and everything gets really fragile. But then basically for like any interesting example that I've encountered, it's well within the bounds of where things still work here.
I was going to say that you kind of need some easy sequence.
Right. Right.
Do you need that to get the minimum? Because my understanding of the pointed set principle is you need to, get like better and better covers, and we can kind of dovetailing of all these into one cover.
Mhm.
Right? That's how you get a minimum in your counter set, right? But if you just want it like an increment, then you don't need to do this obtaining that much. So maybe you need less conditions on your knowledge conditions before you do a lot less. If you're happy with your thing, which probably then is internally enough for your theorem.
That is possible. I'm not sure. Okay, so we have a application of this more general point set principle to the hyperspace of compact sets. So if you have a metric space X row, then you can look at the space of all non-empty compact sets within that space under the Hausdorff metric, where you just look at basically the farthest away that 2 points can be within these sets. And this is separable because the set of all non-empty finite subsets of X is a countable dense set here. So that means that we'll be able to apply our point set principle to this, and we need to do it in a gauged way because I mean everything here is very infinite dimensional. So in order to quantify dimensions in a meaningful way here, we need a really aggressive gauge family. So let's back up to here. I guess. No. Okay, so I mean, basically we need, because the number of cover elements is going to be blowing up really, really fast, we also need some phi s, or some phi that's like shrinking aggressively fast as you get close to zero to balance that out and give you some meaningful trade-offs there. Okay, so let's let phi, let's let psi be the gauge family 2 to the -1 over delta to the s. Okay, so this differs from the standard gauge family that's just delta to the s, and is much more aggressive. And McClure proved that if E is a self-similar set, then the psi-gauged Hausdorff dimension of the hyperspace of compact sets is equal to the Hausdorff dimension of the underlying set. So we can define more generally this jump transition from gauge function phi s to jump phi s of delta, which is 2 to the -1 over phi sub s of delta. So this is a way to make any gauge function exponentially more aggressive. And for example, this psi above is just the jump of the standard gauge family delta to the s. So here's our more general theorem. If you have any separable metric space and you have a gauge family, then so this is the first hyperspace dimension there, just for Minkowski dimensions. That in general, taking this jump gets you to the hyperspace of compact sets with the same upper or lower Minkowski dimension. That balances that out exactly. So McClure's theorem follows as a corollary here, because remember that was about Hausdorff dimension, but it was about self-similar sets. And I said that for self-similar sets, the Hausdorff dimension and Minkowski dimensions coincide. So this gives that. And then we can also say something about packing dimension here, that if E is a compact set, then taking the jump sorry, if it's a compact set, then the packing dimension and the upper Minkowski dimension of jump phi of the hyperspace of compact sets coincide. And furthermore, if E is analytic, then the jump packing dimension of the hyperspace of compact sets is at least the packing dimension of the underlying set. But this inequality can be strict, and you also could have strict inequality in the case of Hausdorff dimension. So that says that even for analytic sets, McClure's theorem can't be extended completely. Okay, so yeah, that's one of the directions of extension here, and we'd like to see more extensions into other interesting metric spaces. But now I want to talk about point set principles for complexity classes. So in the point set principle, if you have a computationally strong oracle W, then you could use a computationally restricted version of Kolmogorov complexity over on the right side. Right, like you have this really strong oracle that's helping the Turing machine that's doing the decoding. So that Turing machine could actually be computationally weak since it has access to this oracle. So, for example, we noticed that you could just require that Turing machine to be polynomial time bounded, and this would still hold. So that suggests that maybe there are resource bounded instances of the point set principle that we could use to study computational complexity classes. Okay, so here's what I mean by resource bounds. So we can talk about all, just the all functions. We can talk about computable functions. P is P1 is functions that are computable in polynomial time. QP is computable in quasi-polynomial time. We can continue up a hierarchy to P3, et cetera, and also define PI space for all I greater than or equal to 1. And then we can take any of these relativized to set or function oracles. Okay, so that's what I mean by resource bound here. And then we'll also need result classes. So a constructor is a function delta such that delta of W is a proper extension of W for all words W. And the result of a constructor delta is the unique sequence R delta such that delta is the in-wise application of delta to the empty string lambda is a prefix of R of delta for all n. So the result class of a resource bound then is the class R of big delta that's all results of constructors in that class. So for example, R of all is the entire Cantor space. R of comp is the set of decidable languages. R of P is E, and R of QP is exp. And then here we are going to do dimension via Gales instead of via Kolmogorov complexity. So this is the way that dimensions were originally defined. Kolmogorov complexity has been a more useful way to look at it in some settings, but here we use Gales. So an S-Gale is a function delta such that, sorry, it's a function D, such that D of W is 2 to the minus S times D of W0 plus D of W1. So this generalizes martingales, which are just 1 Gales. And we say that an S-Gale succeeds on a language if, as W approaches A, you can make infinite money betting on it. So D of W goes to infinity in the limb soup. Okay, and then we can define for any subset of Cantor space this G of X to be all the S's such that some S-Gale succeeds on X. So this is saying how unfavorable the betting environment can be and still allow you to make infinite money when betting on X. So then the Hausdorff dimension of X is the infimum of this G of X. It's an alternative characterization. Okay, so with that characterization, then it becomes more straightforward to do resource bounds, resource bounded versions of this. So if you have some delta that's a resource bound, and you have X is a subset of the Cantor space, A is in the Cantor space, then S is in G sub delta of X if and only if there's some delta computable S scale that succeeds on X. So we've just applied that resource bound directly. We can say that the delta dimension of X is the infimum of that G sub delta of X. The delta dimension of X in R of delta, in the result class of delta, is just the delta dimension of X intersect the result class. The delta dimension of A is just the delta dimension of that singleton. We say that S is in G sub alg of X if there's some lower semi-computable S scale that succeeds on X. And the algorithmic dimension of X is the infimum of G alg of X, and the algorithmic dimension of A is the algorithmic dimension of that singleton. Okay, so with these resource bounds, we have a partial order where for all pi, this hierarchy from polynomial to quasi-polynomial and so on, pi is less than pi plus 1 is less than comp. Same is true for space. Pi is less than or equal to pi space, and comp is less than all. So in general here, we have that if gamma is less than delta in this order, then delta parameterizes gamma. In the sense there's a function f in delta where gamma is fk such that k is an n, where fk is the kth slice of f. So basically delta is capable of enumerating everything inside gamma. Okay, so with all that, here's our point set principle for resource bounded dimensions. If you have these two resource bounds with this relationship that delta parameterizes gamma, then you have that the delta dimension of X is the minimum over function oracles G and delta of the supremum of A and X of the gamma dimension of, the gamma dimension relative to G of A. So for example, this tells us that the Hausdorff dimension of X is the minimum over all oracles of the supremum of points of the P dimension relative to G of A, which is just what I said before, that we could restrict to polynomial dimension, polynomial time dimension on the right-hand side without affecting anything because the oracle G is sufficiently strong to compensate for that. This is also true though for QP dimension, that the QP dimension of X is the minimum over QP oracles of the supremum of the P dimension relative to G. And that's actually the instance that we'll use for an application here. So we use this for to study selectivity. For a resource-bound delta, a language is delta selective if there's a selector function such that for all pairs A and B, we have that this function of AB is in AB, and if A is in A or B is in A, then f of AB is in A. So what that's saying is that if only one of F's two inputs belongs to A, it has to correctly identify which one. So this is something easier than actually computing the functions. So every language, A and P is p-selective, but there are in fact uncountably many p-selective languages. So the converse doesn't hold. So we're going to look at notions of hardness for X. So let's let Pm of H be the set of all A such that A is polynomial time many one reducible to H. And then say that H is Pm hard for X if X is a subset of Pm of H. And we can then weaken this notion by saying that H is weakly hard for exp if the measure of PM of H within exp is positive. So it doesn't necessarily contain all of X, but it contains some positive measured part of X. So that's the same as saying that no QP computable martingale can succeed on PM of H intersect exp. And we can further weaken that by saying, okay, what if we didn't try for positive measure, we just try for positive dimension there? Because there are measure zero sets of every dimension. So positive dimension is a very weak condition. So what if we have that H is partially hard for exp if the dimension of PM of H within exp is positive, meaning that there's some positive S such that no QP computable S scale can succeed on PM of H intersect exp. Okay, so that's a strictly weaker notion than weak hardness. Okay. So here's what we can prove about selectivity. First, okay. So going back, Selman proved that no p-selective set is hard for exp. Then Berman and Longpre and Wong independently proved that no p-selective set is weakly hard for exp. So we can improve that along two axes by showing that you can change P to QP there and change weak hardness to partial hardness. Okay, so we're going to do that via the point to set principle. Here's how this goes. So first we're going to show that PG selectivity implies PG dimension 0. So if you have some B and some function G, if B is PG selective, then the P dimension of B relative to G is 0. And an easy extension of that is also if you have some A that is reducible to B, then you still have dimension 0 there. So here's a very loose proof sketch of that. That we're going to take some positive S and we'll build an S scale that succeeds on B and runs in polynomial time relative to G. That's sufficient to show that it has dimension 0. That was the definition that we had. So what we'll do is take a block of K strings where K is a large constant that depends on X, and then we'll query the selector for B on all K squared ordered pairs, right? If B is selective, we have this polynomial time selector relative to G, and we have all these ordered pairs, and we're just going to bet on the strings that are selected more often. And by doing that, we can run in polynomial time with access to this oracle G, and we can make money over time, thereby showing that this martingale or this S scale succeeds, and that it therefore has dimension 0. Okay, so using that, then we can prove this thing I asserted, that no QP selective set is partially hard for exp. So let's let QP prime be the set of all functions in QP whose output length is polynomially bounded, and let H in QP prime be something such that QP prime is P to the H. Then let B in QP, let B be QP selective. So that tells us that B is pH selective, because a selector doesn't have long output, so B is yeah, QP prime is sufficient there. So this is also pH selective. Then what we want is for the dimension of PM of B in X to be 0. Now, by definition, we have that the dimension of PM of B within X is the QP dimension of PM of B intersect X, which has to be less than or equal to the QP dimension of PM of B by monotonicity. And we know that for all A in PM of B, the previous slide tells us that the P dimension of A relative to H is 0, right? Because we said that if A was reducible to B, B was PH in this case selective, then the P dimension of A relative to H was 0. Okay, so then we can apply the point to set principle and say that the QP dimension of PM of B straightforwardly is the minimum over all these function oracles in QP of the supremum of A and PM of B of the P dimension relative to G of A. And on the previous line, we just showed that, sorry, and then H is less than or equal to this, and sorry, the P dimension of A relative to H certainly is greater than or equal to that minimum, and we showed on the previous line that all of those are 0. So that proves the theorem. Okay. So, I mean, what we have here is some results that are amplifying and exhibiting the power of the theory of computing to make unexpected contributions to other areas of the mathematical sciences, both, more general geometric measure theory, and then also, porting back to complexity theory in some unexpected ways. So we hope and expect to see more such results in the near future. These seem to be really broadly applicable modes of reasoning. So I want to call it 3 specific open questions. The first is that in the hyperspace packing dimension theorem, does E actually need to be analytic? So as I said, a lot of the successes of this have been in removing assumptions of being analytic from theorems, but we still have that there, and it's unclear whether that's really necessary. We'd also like to know, is there a corresponding hyperspace Hausdorff dimension theorem? That turns out to look more difficult. And then we'd like to know how we can characterize algorithmic dimensions in separable metric spaces in terms of martingales or more general gales. Because remember, for that part of this, we were still working in Kolmogorov complexity, and it may be useful to work in gales there. Thank you.
Very much. Are there any questions?
So my question is whether the definition of the bounded resources algorithmic dimension is only in terms of martingales or gales, whatever, or there is also a algorithmic information characterization of that one?
The resource bounded version has only been done with gales. Oh, for space bounds, you can. Oh, okay.
So the point is time. I mean, when you make some time bound assumption, then you have to work with the. Okay, thank you very much.
Be ways around relate to the concept.
So my question is about the choice of the dense set and or rather the dense sequence, because the order might matter, right? When you're generalizing effective dimension to generous separable spaces. Your theorem then kind of seems to show that that doesn't matter up to some oracle, But do you have anything sort of better that is there a nice characterization that maybe shows that the kinds of sequences you would reasonably pick all gives the same algorithmic that dimension, or does the stuff vary wildly then?
So yeah, we fixed an function up front for enumerating the dense set. I don't think we have any crisp characterizations of when that would matter. I don't know. What do
You can be all right with what, yeah, I'm not completely sure.
I mean, to say, so one example for just the standard Euclidean space could be, well, if you're using dyadic rationals rather than all rationals, or maybe you're using sort of another computable enumeration of it, just a dense set of reals. I mean, that would all give you the same computability theory on that space. But it could obviously sort of, well, but sort of it's not clear to me whether that would change the algorithmic dimension in any meaningful way. Are there points that you can approximate easier by, I don't know, multiples of pi than by rationals, or is it all the same in the end?
So I mean, at least if you're working in a reasonably friendly metric space, where this stuff doesn't get too fragile, I mean, all the differences are going to end up being sublinear, because all these things can be used to estimate each other, and so it's going to, you know, come out in the wash of dividing by r there. But it could be that you could get some really pathological example where it makes a difference.
And the algorithmic dimension could be different, but you have these many cases equivalent. So we haven't decided exactly.
Okay, thank you.
Okay, do we have any more question? Oh, we have to check the online crowd.
Looks like.
Doesn't seem to be the case. Okay, well, we'll thank the speaker again.
Thank you.
So